Have you ever thought about what happens when a multi-million-dollar industrial robot just glitches? It's not always a software bug. A lot of the time it's something way deeper. This kind of hidden electrical chaos that can bring the most high-tech machinery to a screeching halt. Today, we're going to troubleshoot that chaos.
So let's just ask the big question right up front. We've got these amazing machines, right? Robots that perform tasks with unbelievable speed and accuracy. So why do they sometimes just fail? What is it that makes them lose that precision and start messing up?
And the answer, believe it or not, is often right here, an unstable DC bus voltage. Now, you can think of the DC bus as the electrical heartbeat of the machine. It's got to be a steady, solid pulse of power. But when that heartbeat gets all erratic, when you get these chaotic voltage ripples, it's like a cardiac arrhythmia that throws the entire system off balance.
Okay, so to really get our heads around the solution, we first have to understand why this unstable power is such a huge problem for any kind of precision motion control.
This right here, this quote from a servo motor manual, it just lays it out perfectly. It really gets to the core of it. A motor's top speed, its ability to do its job, is directly tied to that DC bus voltage. I mean, that's not a suggestion. It's basically a law of physics for the system.
And wow, this graph shows you exactly what happens when that law gets broken. Look at this thing. This is the position error of a machine with an unstable DC bus. All this chaos, these wild spikes and dips, it means the machine is literally not where it's supposed to be. It's getting commands, but it can't follow them because its power source is just all over the map. Alright, so to find the source of all this instability, we have to go inside the system. We're going to pop the hood and look at the heart of the machine, the servo drive. And here is our roadmap for this little journey. This diagram shows how power gets from the wall outlet all the way to the motor. It flows through a few really critical stages inside this drive, and this is where both the magic and, the problems happen. So it's basically a three-step trip. First, the converter takes the AC power from the wall and turns it into DC. But it's kind of choppy. It's not smooth. That's where step 2 comes in, the smoothing circuit. That's our DC bus. Its whole job is to iron out all those ripples. And then finally, the inverter takes that nice, smooth DC power and creates the exact AC signal needed to control the motor. Our investigation is focused right on that second step, the smoothing circuit. So we know where the problem is happening. But what's causing the instability in the first place? Well, that brings us to this really fascinating, really powerful phenomenon called the regenerative energy effect. Think about this for a second. When you tell a really heavy, fast-moving motor to stop on a dime, it doesn't just stop. The inertia of whatever it's carrying keeps pushing it forward, and in that split second of deceleration, the motor's role completely flips. It stops being a power consumer, and it becomes a power generator, sending a huge jolt of electricity right back where it came from.
And hey, this isn't just some theory. The engineering manuals spell it out in black and white. Because of inertia, the motor functions as a generator, and that power comes flying back to the amplifier. So this isn't a bug, it's a totally predictable and pretty powerful consequence of physics.
So what happens to all that energy that comes rushing back? Well, it has nowhere else to go. It slams right back into the smoothing circuit, our DC bus. You can picture it like a small energy tsunami crashing back into the system. And that flood of power causes a huge, sudden, transient spike in the DC bus voltage. That is the source of our instability. This creates a fundamental challenge in any high-demand automation setup. So how do engineers actually tame these unavoidable voltage spikes and keep the whole system stable? Let's take a look at the tools they use.
The first line of defense is actually built right into the servo drive itself. It's a capacitor. Think of it like a little seawall, designed to absorb the energy from small waves and routine stops. For most everyday tasks, it works just fine.
But what happens when that energy tsunami from a really fast stop comes crashing in? That little seawall gets completely overwhelmed, and that's when you need a second tool. See, the capacitor is a buffer, but for the really big surges, we need a braking resistor. This thing acts like a pressure relief valve, or maybe a dam's spillway. It gives that massive rush of energy a safe place to go by turning it into heat. So the trick is knowing when you need to install that spillway, and the documentation is super clear about it. A braking resistor is absolutely essential in high-demand situations. When you've got a heavy load, when you're doing lots of quick stops, or basically any time the regenerative energy is just way too much for that little built-in capacitor to handle. This is how you prevent those regenerative over-voltage alarms that can shut down an entire production line.
And it's really important to get that these are not just generic parts you can grab off the shelf. This spec table shows that these are precision braking resistors. They're carefully engineered components. They get selected with very specific resistance values and energy ratings, all perfectly matched to the motor they're protecting. It's a very precise solution for a pretty complex physics problem.
So after all that, what's the payoff? After we figured out the problem and put in the right solution, what does success actually look like? Well, it looks like achieving a controlled, linear power baseline.
And this just shows the transformation perfectly. On the left, you've got that chaotic position error graph we started with. That's the machine just flailing around. But on the right, that's the position response with a stable DC bus. Just look at how cleanly the actual position, that dashed line, is tracking the command. That right there, that's a picture of a machine in total control. Ultimately, the goal is this number, 0.
or as close to zero position error as you can possibly get. And having a stable DC bus, where all that regenerative energy is managed correctly, is what makes this number possible.
And the benefits are about way more than just being accurate. As the source material points out, a stable system lets you increase acceleration and velocity, it improves your overall efficiency, it cuts down on the audible noise from struggling parts, and it gives you true disturbance rejection. Basically, the machine becomes faster, stronger, quieter, and way more robust.
So, let's just recap the journey. We started with a system in chaos. We figured out the root cause was regenerative energy flooding the DC bus when the motor slowed down. And by using the right tool, the braking resistor, to safely get rid of that energy, we turned a volatile power problem into a stable baseline, which unlocked true precision motion. And that kind of leaves us with one final thought. We've seen how managing these surges of energy is the absolute key to controlling a high-performance machine. It really makes you wonder, right? Where else are these exact same principles of capturing and getting rid of regenerative energy shaping our high-tech world? I mean, from electric cars to the stability of our entire power grid, this is a fundamental challenge that engineers are solving every single day. Thanks for joining me.
Thank you for viewing. So far, if it gives you some information, hit the like button and subscribe for more such technical learning.